Good afternoon, one and all. Today, we are going to see the problem under the fault condition. So consider a radial network that is shown in the figure. Three-phase fault occurs at the point F. Three-phase fault. Here, this is the single line diagram. So don't ask like how three-phase fault occurs like here. So this is being a single line diagram. So it is represented like this. So here you consider the three-phase fault occurs at the point F. That is a point F. Determine the fault current and line voltage at 11 kilovolt bus under fault conditions. What we need to determine in the sense we need to determine the fault current and line voltage at that particular 11 kilovolt bus. So here you see there are two generators are there, generator 1 and generator 2. Generator 1 having the MVA, that is base MVA as 10 MVA. Here also generator 2 also 10 MVA. Here 15% reactance. Here 12.5% reactance. That is connected to the 11 kilovolt bus. Next, that 11 kilovolt bus is connected to a transformer T1 having the base MVA as 10 MVA and the reactance as 10% reactance. Next, that transformer also connected to some overhead line. Say, for example, that overhead line distance, length of that overhead line is 30 kilometers. The impedance is 0.27 plus J into 0.36 ohm per kilometer. That is Z is equal to R plus J into X. So this is R and S. So together it is a impedance that is in ohm per kilometer. Next, that overhead transmission line passes for 30 kilometers and again it is connected to a 33 kilovolt bus. 33 kilovolt bus. That is connected to again one more transformer, that is transformer T2 having the base MVA as 5 MVA and having 8% reactance. Again, it is connected to 6.6 kilovolt. Okay, and again some cable is there. Cable is of some 3 kilometer long. 3 kilometer long, and we are having the impedance Z equal to 0.135 plus J into 0.08 ohm per kilometer. Consider here the fault is occurring. Consider here the fault is occurring. So this is the thing. So already we have seen how to calculate the base MVA, what is base kilovolt, everything in our previous class. So if you don't follow, I will give that a link in the comment so that you can click and you can also know how this base MVA to be chosen, how this base kilovolt has to be chosen for a generator 1. What is the formula for calculating new impedance value? Like that, everything already we have discussed in the previous class. That I will give the link in the comments. Here, the what now goes to the solution. For what is the first step is to draw the reactance diagram. First, we need to draw the reactance diagram. For drawing the reactance diagram, we need to know what is the impedance of this generator 1, generator 2, what is the impedance of this transformer 1, what is the impedance of this transmission line. Transmission line already given. So what is the impedance of this transformer 2? Like that, everything we need to calculate, that is new impedance of that particular line. So like everything we need to calculate. After that, we need to draw the reactance diagram. After that, we need to find out the fault current in that particular area and what is the bus voltage at the particular bus also given in the problem. So here, before going for the reactance diagram, what is the base MVA given in the problem is 10 MVA. Because why it is 10 MVA? Because here in the two generators are given in the same base MVA value. So 10 MVA. So base MVA we are taking as 10 MVA. Next, the base kilovolt is equal to 11 kilovolt. Base kilovolt is the 11 kilovolt because here the bus is 11 kilovolt. So this is the thing. Next, for generator one, KVB new. KVB new value is nothing but 11 kilovolt. What is the KVB old value? Old value or given value is also 11 kilovolt because there is no previous value. So old and new values are same here. So that you need to remember always while solving the problem. So KVB new is equal to 11 kilovolt. So generator one. So how to calculate this new impedance Z new is equal to Z old or Z given into KVB old divided by KVB new the whole square into MVA B new divided by MVA B old. So this is the formula for calculating the Z new. So here just a substitution Z old. What is the Z old? Now already it is given in the problem, that is generator one, it is given as 15% reactance. So we need to take as J into 0.015, that is 15 divided by 100. So here it is J into 0.15 into KVB old. KVB old is 11 kilovolt. KVB new is also 11 kilovolt, the whole square into MVA B new divided by MVA old. So MVA B old new value MVA new value is this new value and old values are same because there is no old values given in the problem. So new value only old value. So here we are taken as 10 new values also 10 and the old values also 10. Okay, so just take your scientific calculator, calculate it, simplify it and calculate it. I think this and this get cancelled and here also 11. So here you can get direct answer as J into 0.15 per unit. So because new value and old value, KVB new and KVB old value are almost same. So so if some problem they will be given the take the old old value as like that they will be given. In that case, this will be changing. So in that case, you'll get different answers here. So directly answer J into 0.15 per unit. Next, similarly for generator 2, KVB new is equal to 11 kilovolt same. MVA also 10 MVA. So here same formula Z new is equal to Z given into KVB old divided by KVB new the whole square into MVA new divided by MVA old. Okay. So here you need to substitute all the values. Here given value, what is the old value or given value in the generator 2 is here 12.5% reactance. So 12.5 divided by 100 is 0.125 J, 0.125 J. So that is the reactance, that is J into 0.125 into this old old value and new value. So here 11 divided by 11, the whole square into MVA new divided by MVA old. That is 10 divided by 10, 10. So that is equal to, just simplify it. I think this this and this get cancelled. This and this also get cancelled. So direct answer you will get as J into 0.125 per unit. So Z new value. That is the for generator 2. Next, coming to the transformer one. So you need to follow, don't follow blindly here. You hear whatever is there that you need to calculate. So after two generators, you need to calculate for transformer number 1. So what is the reactance given? 10%. That is 10 divided by 100 is 0.110 J. So that is the reactance that is given. So here for transformer, also what is the formula? It's the same formula. That is already. So Z mu is equal to Z old into this KVB old divided by KVB new, the whole square into MVA new divided by MVA old. Okay, so here just as you need to substitute here KVB new and old are same values, that is 11 kilovolt. and MBA new and old are same values 10 MBA. So here just substituting, simplifying. So this and this get cancelled, this and this get cancelled. So you'll get the direct answer as J into 0.1. So in exam, you can save your time. So somebody will what they will do is they will simply type this all the things in the scientific calculator. Then they will go for simplification. Then again the same answer will come. So then you will tell like time will be not sufficient for solving the problem. No. So you need to be very use your presence of mind every time so that the time also will be saved. Next, after that, after transformer number one, next is transmission line. Transmission line, what here the transmission line is there over a transmission line 30 kilometers. So Z is equal to 0.27 plus J into 0.36 ohm per kilometer is the impedance given. So now transmission line. So KVB new. So new KVB is equal to 33 kilovolt because already given how it is 33 kilovolt means it is connected to the this 33 kilovolt bus. So the base kilovolt is 33 kilovolt. So you should not take the previous value. So it previously it is 11 kilovolt. So you can take 11 kilo. No. So here 33 that overhead transmission line is connected to 33 kilovolt bus. So you need to take this base value as 33 kilovolt only. So you need to be very careful while solving this problem. If you wrongly choose some other value, then the answer may goes wrong. The total whole problem will goes wrong. So 0 marks only for step marks, 1 or 2 marks only they will give. So 0 marks only you will get out of your 10 marks. So you need to very careful while solving this problem. Here you see the transmission line. Yeah, 33 kVB new is equal to 33 kilovolt. So here, what is the this Z new is equal to Z actual divided by Z base. So Z actual divided by Z base is nothing but already this formula also we have seen before for transmission line. What is the formula that we have seen in the before? I will give you that that video link also in the comment, so you can watch those and you can get it clarified. Okay, so this is not anything for any new formula you need to memorize or something. Already we have seen how this is it like is a new should be calculated for your transmission line. Already formula we have seen in our previous classes. So what is Z actual? Z actual is equal to this is given in the problem itself, that is 0.27 plus J into 0.36 ohm per kilometer. So per ohm per here it is given as ohm per kilometer, but how much kilometer, that is also given in the problem. How much kilometer is 30 kilometers. So simply you need to multiply by 30. So whatever the impedance value, that is into 30. So you'll get Z actual value in ohms. So it is in ohms per kilometer. We are converting that into ohms. So Z new value. So what is the Z new value? So Z new value is equal to Z actual, that is 0.27 plus J to 0.36 into 30 divided by this KVB squared into MVA base. So here KVB squared, that is KB base squared is equal to 33 kilovolt. Already we have seen 33 the volt squared into MVA base. MVA base is 10 MVA base. Because already we have seen take the base MB as 10 MB. So just you have to simplify. Now you simplify with your scientific calculator, you will get the answer as 0.0744 plus J into 0.0992 per unit. So always you need to remember this is in the per unit. If you simply don't put the unit here and solve the whole problem, they will cut 2-3 marks or 4 marks only for not keeping your units. So whatever the units is there, say for example, here is in kilovolt, then here base MVA, here it is in per unit. So unit you need to always mention then and that. Next, coming to the transformer number 2, this is the ZU value for this transmission line that you already calculated. Coming to the transformer number 2, what is the base kilovolt new? That is 33 kilovolt. That is a primary side that is given in the problem. So base kilovolt new is equal to 33 kilovolt. That is the primary side. So Z new is equal to same formula, Z volt into KVB volt. KVB volt divided by KVB new, the whole square. Next, into MVA new divided by MVA volt. So here you need to substitute. This is the formula, just you need to substitute. So here KVB new and KVB volt are same, that is 33 kilovolt. So 33 by 33 the whole square into this thing, that is base MVA, base MVA new, MVA new divided by MVA volt. So MVA new is 10 divided by 5. So here how it is 5, because here, yeah, the transformer itself it is given as 5 MVA. So that is the old value. So whatever is given in the problem, that is the old value. So new values, whatever the thing previously we considered. So previously we considered the new value as that is base MVA as 10 MVA. So that we have taken here. So 10 divided by 5. So just you just simplify it with the scientific calculator. This and this get cancelled. So this becomes 2. So the 2 into J into 0.08 is 0.16 per unit. That's all. So transformer 2, you get the answer. Next is what? You need to see the single line diagram. Next, after the transformer, it is some cable for 3 kilometers. So here also impedance is given. Z is equal to 0.135 plus J into 0.08 ohm per kilometer. Next, what the same thing, whatever we did in the previous overhead line, that is Z actual is equal to 0.135 plus J into 0.08 ohm per kilometer, that is given in the problem. What is the kilometer range given in the problem is a 3 kilometer range that is given in the problem. That is that cable is of 3 kilometers long. So this is in ohm per kilometer. So to convert that into ohm, so what we need to do, you need to multiply that with the whatever the kilometers given. So here the kilometers given in the problem is 3 kilometers. So just you need to multiply, simplify with your scientific calculator. That is will be the answer for that Z actual, or just take it as it is because we are going to solve here. Next, what is KVB new? KVB new is equal to here the same formula. KVB sorry. Yeah, here the KVB new is equal to 6.6 kilovolt. So 6.6 kilovolt because this transmission line is connected to this 6.6 kilovolt. So KVB new is equal to 6.6 kilovolt. 6.6 kilovolt. Next, so new Z new is equal to Z actual divided by KVB squared into MVA base. So Z actual what already we calculated, that is 0.135 plus J into 0.08 into 3. That you need to substitute here, divided by KVB squared. KVB squared is KVB news is 6.6. So 6.6 squared into MVA base. So MVA base is 10 MVA. That already you know. Just you need to simplify this. You'll get the answer as 0.093 plus J into 0.055 per unit. So Z mu is equal to 0.093 plus J into 0.055 per unit. So now we have calculated the impedance for all the equipments, that is equipments that is given in the single line diagram. that is connected in the single line diagram. That is G1, G2, transformer 1 overhead line, next transformer 2, next cable. So everything we calculated. So easily you can solve this problem and you can calculate. After that, what you need to do is you need to draw the reactance diagram. Reactance diagram, how to draw the same as like that there it is in your single line diagram. So single line diagram, you see two generators are there. So that is connected with all in a series. Say for example here two generators. What is the impedance already we calculated as here from generator 1, that is J into 0.15 per unit. Generator 2, J into 0.125 per unit. The same thing you need to mention here, 0.015 J into 0.0125. So voltage, what is the voltage here? 1 at the angle of 0. Here also 1 at the angle of 0. That is, we need to start with a flat start, and also in the generator, we are taking the voltage as a flat voltage. That is a flat start. That is 1 at the angle of 0 or 1 plus J0. Anything is okay. So here next comes what after your generator 1 and generator 2 comes the transformer number 1, next transmission line, next transformer 2, next cable. So all are in series. So J into 0.1 is in series. Next transmission line, this value, that is 0.0744 plus J into 0.0992 per unit, that is also in the series. Next transformer 2, what? Yeah, this is the value. Z mu is equal to J into 0.16. Next for cable, what is the new impedance value is 0.093 plus J into 0.55 per unit. So simply we are connecting all the impedance in the series with this two generators. So here J into 0.1, J into 0.0744 plus J into 0.0992. Here J into 0.16. Here J into 0.093 plus J into 0.55. So here you consider the fault is happening in the single line diagrams, same place the fault is happening. So here you can consider this, the fault is happening here. Next, what we need to do is we need to further simplify. It is like a like impedance connected in the series. So impedance connected in the series, you need to add all the impedance. What are all the impedance connected in the series? Just you take your scientific calculator and add all these things. You will get the answer like 0.1674 plus J into 0.4142. You just tell in comment whether you also got the same answer or not, or whether you are getting some different answer also. That is also you have to tell in comment so that we can verify easily. Next, what we need to do is, yeah, here 0.15, here same thing is that, because this alone we simplify, that is connected in the series. This alone we simplify. It is the same as that of your resistance. That is here J into 0.15, here J into 0.125. So here 1 at the angle of 0 degree. So here you are considering the fault is happening. The fault current is flowing as IF. Next, further simplifying. So because these two reactants are connected in the parallel, no. So further simplifying, how to simplify this? 1 divided by J into 0.15 plus 1 divided by J into 0.125, or otherwise in the other terms, J into 0.15 into J into 0.125, the whole divided by J into 0.15 plus J into 0.125. So further simplification, you will get the answer as J into 0.068. Next, here, what is the impedance connected here? J into 0.164 plus J into 0.142. That is carry over from here. So here what you need to do is you need to further simplify, because these two are connected in series now. So further simplification, you'll get the Thevenin voltage as 1 at the angle of 0, and here the voltage, or sorry, here the resistance or your reactance here value here is because this you need to add here. So just J into 0.1674 plus J into 0.4822. So this is the impedance we got here. That is this is the voltage source, and one impedance source, we got the impedance. So here it is not J, it is printing mistake. So 0.1674 plus J into 0.4822. That's all. So this is the thing. Now we need to calculate the fault current. What is the fault current? Already we have explained in the previous class like how to calculate the fault current. That is E Thevenin divided by Z Thevenin. E Thevenin what? 1 at the angle of 0. So divided by Z Thevenin what? So the for simplified value here, the simplified value here is the same thing. You need to copy and paste it over here. So here 1 at the angle of 0 plus divided by 0.1674 plus J into 0.0 J into 0.4822. Further simplification, you'll get the answer as 0.6425 minus J into 185. So here this complex form is further converted into polar form as 1.959 at the angle of minus 70.85 per unit. This is the fault current that is happened here. That is the fault current IF. What is the base current? What is the base current in the sense MVA divided by √3 into KVB? That is the base current IB. So this also already we have seen this formula how it comes like that. So that also you go back to my previous videos and just you need to find out how to calculate the base current. Here MVA base is 10 into 10 to the power of 3. That is 10 MVA divided by √3 into KVB. So KVB is nothing but 6.6 kilovolts. Further simplification, you will get the base current as 874.77. 874.77 amperes. Next, how to calculate this fault current is fault current, how to calculate? Yeah. So here 1.95. So how will this 1.95 come is here fault current IF into this base current. So whatever the base current here we calculated that into this IF. Okay, so that you need to substitute over here. So 1.959 at the angle of minus 70.85 into 874.77. 874.77. That is, you'll get the answer as 1714 amps. That is a fault current. Next, this is the fault current we need to calculate. That is already asked in the problem. So to determine the fault current. So just you need to multiply, you'll get a 1714 amperes. This is the fault current at that particular fault. Next, we need to calculate the voltage at 11 kilovolt bus. So voltage at 11 kilovolt bus is exactly like here. So in single line diagram here, 11 kilovolt bus, but in the reactance diagram, it is exactly like here. So what we need to do is, or otherwise here. So you need to further simplify. You get have the answer already. That is 0.1674 plus J into 0.4822. That answer already you are having here. So here further you need to convert that into your polar form. Polar form you'll get 0.447 at the angle of 67.99 degree per unit. So that is the voltage at the 11 kilovolt bus. So now we calculate the voltage at the 11 kilovolt bus. So that is nothing but ZAF. Sorry. Previously, this is the ZA, that is the impedance at the point impedance at A to F. So why we are taking A to F? Now, here we are taking some this particular node as a and this fault happens as F, like that we are taking. So ZAF is nothing but all this reactance, all this impedance we need to simplify and we need to make it 1. So here already we did and we make it to 1. That same answer 0.1674. The same answer here also we are keeping. And further voltage at 11 kilovolt bus, how to calculate ZAF per unit into IF per unit. So ZAF per unit, this is the value that is 0.447 447 at the angle of 67.99 into IF per unit. So fault current per unit. So fault current per unit we already calculated, that is 1.959 at the angle of minus 70.85. So that you need to substitute, take your scientific calculator, calculate it. You will get the answer as 0.874 minus j into 0.0436. So that is nothing but nearly equal to 0.875 per unit, because here you get a minus 0.047. So merely it is 0.875 per unit. Now, what we need to do is voltage at the 11 kilovolt bus. We need to convert this per unit into voltage. So for that, what we need to do, you need to multiply with the base voltage. So what is the base voltage that is taken in the problem is 11 kilovolt. So just you need to multiply this, that is 0.875 into 11. So you'll get the answer as 9.615 kilovolt. So this is the voltage at the 11 kilovolt bus. So they need to, what they said, we need to calculate the fault current IF, determine the fault current and the line voltage at the 11 kilovolt bus. So where you may occur, you may incur the mistake in the sense here base kilovolt. While choosing the base kilovolt, always you need to check whether that say for example this transformer, which transformer it is being connected, like that. Once you need to check. So blindly if you take okay, this is the 11 kilovolt as base volt for all, no. So here also some base kilovolt is that 33 kilovolt. So that also you need to take into account. So every time you need to check carefully, and you know, the problem and calculation is very simple, and formula everything is simple. But what really you need to do is you need to substitute the correct value. Like you need to substitute the current value, or otherwise the entire problem goes